It's lovely to have you here. Before we begin, I'd love to know where in the world are you watching from tonight? A quiet bedroom, a sleepy train ride, a cozy couch with a warm cup of tea. Wherever you are, I hope you're comfortable, safe, and ready to gently drift into thought. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel float along. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake. But if it does, at least you'll have a better understanding of why particles sometimes act like waves, and why reality seems to hesitate until someone's watching. A small price to pay for a restless night. So, let's begin, shall we? What is quantum physics? And why does it so often sound like the universe is making things up as it goes? The world we know, the one we can see and touch, feels solid, predictable. If you drop a teacup, it falls. If you flip a coin, it lands. If you close your eyes, the moon does not vanish. But in the early 20th century, scientists began to look closer, much closer. And the deeper they peered into the workings of matter, the stranger things became. Light, they discovered, could behave like both a wave and a particle. Particles, it turned out, could exist in many places at once until they were measured. And the act of observing something didn't just reveal what was already there. It seemed to change it. This wasn't a quirk of bad data or fuzzy equipment. It was real, reproducible, and it shattered the tidy laws of classical physics that had held for centuries. Quantum physics wasn't just a new branch of science. It was a new way of seeing reality, a strange and shimmering one where certainty is replaced by probability. And cause doesn't always precede effect in the way we expect. In this video, we'll drift gently through that world. There's no need to grasp every equation or memorize every name. We'll move slowly, softly, one mystery at a time. From the earliest puzzles that nudged scientists off their classical perch to the modern questions that still keep physicists up at night. So tuck yourself in, close your eyes if you'd like, and let's begin to explore a world where even emptiness isn't really empty. At the turn of the 20th century, physics felt almost complete. The laws of motion were understood, thermodynamics was tidy, and light was nicely tucked into the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even believed that all the big questions had already been answered. Only a few odd bits remained to be cleaned up, like dust in the corners of a well-swept room. One of those dusty corners involved a very simple idea. What happens when you heat up an object? When you warm a piece of metal or a lump of coal, it glows. First red, then orange, then white, depending on the temperature. This glow, called black body radiation, comes from how objects emit electromagnetic radiation when heated. It was easy to observe, and it seemed like it should be easy to explain. And yet, the math refused to cooperate. Classical physics, using the well-known equations of the time, predicted something bizarre. According to the formulas, as the temperature of a black body increased, it should emit more and more energy at shorter and shorter wavelengths, particularly in the ultraviolet range. The problem? This prediction led to infinite energy at high frequencies. A scenario so impossible and ridiculous, it was nicknamed the ultraviolet catastrophe. No amount of tweaking classical equations could stop the math from spiraling into nonsense. Enter Max Planck. In 1899, Planck was a German theoretical physicist with a reputation for careful thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview, but he was also pragmatic. And when faced with the black body radiation problem, he did something quietly revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't be emitted in just any amount? What if instead it came in tiny indivisible packets, like coins you can't split in half? These packets would represent the smallest possible units of energy. He called these packets quanta. This was a dramatic shift from the continuous view of energy held by classical physics. Instead of a smooth flow, energy would arrive in steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was unimaginably small, but mathematically elegant. When he plugged this idea into his equations, something amazing happened. The infinite energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe, and yet he didn't quite believe it. In fact, Planck himself described his solution as a mathematical trick, a clever way to make the numbers behave, but not a description of how the universe actually worked. He assumed that future physicists would find a better explanation that wouldn't require such odd assumptions. What he couldn't have known at the time was that his trick would become the cornerstone of an entirely new way of thinking. By the early 1900s, light was thought to be pretty well understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved like a wave, an elegant ripple in the electromagnetic field. It bent, bounced, diffracted, and interfered just like any proper wave should. But then came a riddle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should shake electrons loose more effectively. That was the expectation. But that's not what happened. In experiments, scientists found something strange. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even very bright light did nothing at all. Enter Albert Einstein. In 1905, a year often called his miracle year, Einstein published a paper that changed everything. To explain the photoelectric effect, he proposed something bold. What if light wasn't just a wave? What if under certain circumstances it behaved like a particle? Einstein suggested that light was made of individual packets of energy, which he called quanta of light, later known as photons. Imagine a beam of sunlight filtering through a window. It spreads and ripples like a wave, bouncing off dust and glass. But zoom in, way in, and you'd find tiny quanta of energy, each with its own frequency, knocking into atoms, changing the world one collision at a time. This idea of wave-particle duality is one of the strangest in all of physics. Not because it's complicated, but because it challenges the very categories we use to describe reality. But the quantum world doesn't ask permission to make sense. Einstein's photon